Hi everyone, so we continue with Chapter 4, Exponential and Logarithmic Functions. Specifically, Section 4.4, Exponential and Logarithmic Equations. So we're going to start by studying how to solve exponential equations. Take a look at example 4.15, and it says, solve the equation for the variable t. Give your answer accurate to three significant figures. And it's 2 equals Euler's number to the power of 0.0525t. So in these cases, what we need to do is look at the base. So in this case, the base is Euler's number. So we can solve this using the natural logarithm. We can rewrite this equation by doing or applying the natural logarithm to both sides. So that would be natural logarithm of 2 is equal to the natural logarithm of e to the power of 0.0525 times t. And we might want to use a parenthesis just for elegance. Now, if we do the natural logarithm of Euler's number, remember the solution to this is simply the exponent. Therefore, that means that natural logarithm of 2 is equal to 0.0525 times t. And then to solve for t, all we have to do is divide both sides or send this to divide to the other side, however you want to interpret that. So notice that t is going to equal natural logarithm of 2 divided by 0.0525. We plug this into the calculator, and it's approximately 13.2, rounded to three significant figures. So now let's continue with example 4.17. And it says you invested 1,000 euros at 6% compounded quarterly. How long will it take for this investment to increase to 2,000 euros? So previously we did problems like this one using a GDC to find the answer. We'll still need the GDC, but we won't have to use a graph. So let's remember that the formula for compound interest is final amount is equal to the principal times 1 plus the rate divided by n to the power of n times t. So it's 2,000 equals 1,000 times 1 plus the rate, 0.06, divided by 4, because it's compounded quarterly, to the power of 4t. So we need to solve for t. Notice that we can send the 1,000 to divide, so really we have 2 is equal to, and we can add this here, that's going to be 1.015 to the power of 4t. So in the previous example, we used Euler's number, or we had Euler's number, so we used the natural logarithm. Now in this case, we can also use the natural logarithm or the common log if you prefer, but normally these are solved using natural logarithm. So we apply natural logarithm to both sides again, and we get natural logarithm of 2 is equal to the natural logarithm of 1.015 to the power of 4t. And then here we use the properties of logarithms to send this to multiply. So we have natural logarithm of 2 is equal to 4t times the natural logarithm of 1.015, and then we can send everything to divide except t from this side, and we end up with t is equal to the natural logarithm of 2 divided by 4 times the natural logarithm of 1.015. Plug this in the calculator, and it's going to give you approximately 11.64. So this is about 11 years and almost 8 months. So let's continue with example 4.18, and it says, the number of bacteria that causes strep throat will grow at a rate of about 2.3% per minute. Find, to the nearest whole number, how long it will take for these bacteria to double in number. So this is a bit similar to the previous problem, but it's not compounded. A equals p times 1 plus the rate to the power of time. So notice that we could say, it doesn't say how many bacteria there are initially, but it doesn't really matter because whatever numbers you use, you're always going to end up with a 2 here. Notice that if you write 2,000 here equals 1,000 times 1 plus the rate, which is 0.023 to the power of t, you're always going to divide whatever you have here by sending it to this other side. So you're always going to end up with 2 is equal to 1 plus the rate, so that would be 1.023 to the power of t. And then just apply the natural logarithm again to both sides, and we go natural logarithm of 2 is equal to the natural logarithm of 1.023 to the power of t. We rewrite it as natural logarithm of 2 is equal to t times natural logarithm of 1.023. And then finally we have that t is equal to the natural logarithm of 2 divided by natural logarithm of 1.023. And this gives us approximately 30.5. So we would say to answer about 30 minutes. So now let's take a look at example 4.19, and it says $1,000 is invested in an account that earns an interest at an annual rate of 10%, compounded monthly. Calculate the minimum number of years needed for the amount in the account to exceed $4,000. So this is very similar to the previous examples. I would suggest that you pause the video here and attempt to solve the problem on your own. So this would be the solution. Now let's take a look at example 4.20. And it says a 20-gram sample of radioactive iodine decays so that the mass remaining after t days is given by the equation A of t equals 20 times e to the power of negative 0.087 t, where A of t is measured in grams. Find how many days, to the nearest whole day, it will take until there are only 5 grams remaining. So again, this is a very similar problem to the previous ones. Again, I suggest you pause the video here and solve it on your own. So here is the solution. So next we have example 4.21, and it says solve for x in the equation 3 to the power of 2x minus 18 equals 3 to the power of x plus 1. Express any answers in exact form. Okay, so first of all, let's rearrange this. Notice that we can write it as 3 to the power of 2x minus 3 to the power of x plus 1 minus 18 equals 0. Whenever you see a 2 in an exponent, suspect that you have a quadratic function. Notice that we can rewrite it as 3 to the x squared minus 3 to the 1 times 3 to the x minus 18 equals 0. So these are just power rules that I'm applying. Now to get a better picture, we can say let y equal 3 to the x. So we can rewrite this equation as y squared minus 3y minus 18 is equal to 0. And then this is an easy quadratic to solve because it's going to be y minus 6 times y plus 3 is equal to 0. So y equals 6 or y equals negative 3. But before we said that y is 3 to the x. So in other words, 3 to the x equals 6 or 3 to the x equals negative 3. Now this is not a solution because you cannot elevate 3 to any power. That would be a negative, right? So this is no solution. We have to solve for this. So I'll work it out here on the left. Notice that I can go natural logarithm of 3 to the x is equal to the natural logarithm of 6. And then we have a solution, right? We know that x is equal to the natural logarithm of 6 over the natural logarithm of 3. And it says that express the answer in exact form. So we have to leave it like this. This is exact form. So next, we're going to take a look at solving logarithmic equations. And we will start with example 4.22. And it says solve for x in the equation log base 3 of 2x minus 5 equals 2. So since this is a logarithm, we're going to use property number 3. And we can rewrite this as 3 to the power of log base 3 of 2x minus 5 is equal to 3 to the power of 2. As long as I use 3 as the base on both sides, the equality remains true. So this here is base 3. Okay, so now this is going to be 2x minus 5 equals 9. And then we have that 2x equals 14, and therefore x is equal to 7. So this would be the solution. So let's continue with example 4.23. And it says solve for x in terms of k in the equation log base 2 of 5x is equal to 3 plus k. So the base is 2. Then we write 2 to the power of log base 2 of 5x is equal to 2 to the power of 3 plus k. So this is going to be 5x is equal to 2 to the 3 times 2 to the k. And then we can have that x is equal to 8 over 5 times 2 to the power of k. Now remember that we cannot multiply 8 times 2 here because 2 is elevated to the power of k, which is a variable. So this would be the solution for x in terms of k. So now let's take a look at example 4.24, and it says solve for x in the equation log base 2 of x plus log base 2 of 10 minus x is equal to 4. So notice that here we have two separate logarithms, and we know that we can turn the sum of two logarithms into a logarithm of the multiplication of what they have inside, so to speak. So we can rewrite this as log base 2 of x times 10 minus x is equal to 4. And then from here, we're going to get that log base 2 of 10x minus x squared is equal to 4. And then we elevate both sides, right, with base 2. So 2 log base 2 10x minus x squared is equal to 2 to the power of 4. And then from here, we obtain that 10x minus x squared is equal to 16. And then rearranging, we're going to get x squared minus 10x plus 16 is equal to 0. Then we can factor this, and it's going to be x minus 8 times x minus 2 is equal to 0. So the solutions would be x equals 8 or x equals 2. So we're going to end this video with example 4.25. And it says solve for x in the equation natural logarithm of x minus 2 plus natural logarithm of 2x minus 3 is equal to 2 times natural logarithm of x. So we can simplify this using the properties of logarithms, and we will get that natural logarithm of x minus 2 times 2x minus 3 is equal to natural logarithm of x squared. And then we can take this from here and say that x minus 2 times 2x minus 3 is equal to x squared. Let's expand here on the left, and we're going to get 2x squared minus 7x plus 6 is equal to x squared, and then x squared minus 7x plus 6 is equal to 0. From here, we factorize and we get x minus 6 times x minus 1 is equal to 0. Therefore, the solutions are x equals 6 and x equals 1. But we have to be careful. This is a false solution because if we plug 1 into the logarithms, notice that we would get natural logarithm of minus 1 plus the natural logarithm of minus 1 is equal to 2 natural logarithm of 1. So this is where there's a contradiction, right? There's no such thing as the logarithm of a negative number. So that means that the solution is x equals 6 and x equals 1 is what is known as an extraneous solution.